Welcome to my favorite unit in this course, and that is the one on geometry. We're going to be looking at some basic Euclidean geometry. We're not going to get into proofs, so any of you who are thinking back to high school geometry with Euclidean geometry, many of us had to do proofs in high school. We don't have to do that here. We're just going to look at basics, and we're going to look at area, perimeter, surface area, volume, stuff like that. So it's not going to be too in-depth, but it's my favorite. I love geometry. So, moving in. First, we're going to be setting up a lot of terminology and looking at some problems, trying to make sure that we can apply the terminology well before we get into doing anything with polygons and formulas. Alright, so the word geometry, if you break it down, geometry. That's what the baby acorn says when it grows up. Anyways, I have bad jokes, I'm sorry. I'm a tree. Alright, it literally means earth measure. Geo for earth and metry for measure. And so we're going to be making sure we know how to measure things on the earth. This area of mathematics has been in use as far as records are concerned, as far back as the ancient Egyptians and even before them, because people had to develop mathematics enough for ancient Egyptians to use it to build the pyramids. But anyways, it's probably just as soon as the first humans were walking around, it was a matter of being able to tell shapes of things. That's geometry too, but being able to distinguish shapes and look at trajectories of how fast that cheetah is running and what angle can I go at. I know that shape is a cheetah. What angle can I go at to disappear and not get eaten? That kind of thing. But anyways, ancient Egyptians we know were using geometry. And by the time humans had progressed to the ancient Greeks, this is still BC, ancient Greeks, we had developed mathematics enough that the Greeks could take geometry further than just applying it, and then also advancing it to a field where logic could be applied. So it became a different level of thinking in mathematics at that point. So around 300 BC, we have the Greeks, and especially the Greek mathematician Euclid, for which Euclidean geometry is named. He wrote his set of 13 books called the Elements. In these books, he summarized the mathematics that was known at the time to folks in the area, and he laid the foundation for the planar geometry that we know today. He started with things called these undefined terms like point, line, and angle. Just gave a term for what a point was, what a line was, what an angle was. Things that don't really exist on the earth, but you still have to have them as a foundational area to start from. Using those terms, he built on those to create definitions, things like defining what a triangle is, defining what shapes are, stuff like that. Then to make statements about these undefined terms and these definitions, you could make these statements that were obviously true, called postulates or axioms. They were not proven. They were just statement of fact. Did not need to be proven. You could tell. And then theorems were the next step after that. Those are more developed statements that could be proven. So that needed to be proven too. And whenever you have a theorem, it's not something that can be that mathematicians are comfortable applying to every situation if it hasn't been proven yet. A proof shows, hey, this is going to be true no matter what the numbers, no matter what the situation or scenario. So this is what we're diving into today. Alright, so these undefined terms, I just mentioned them, but what are they? They don't actually exist. You can't actually have them because just by their very nature it's not possible in our physical world. But we can still think about them and use them as a springboard for developing other concepts and things that do exist. Alright, so a point. What's a point? Think about it as like a dot that has neither width, depth, or breadth. Obviously that can't exist in our world because any dot you make in our world is going to have a radius. Even if you make it as teeny tiny as you possibly can, the radius could still be measured even possibly down like to the atomic level. So, but think of a point that it exists, but you can't measure it because there's no radius, of any kind. Then if you take points and you start stringing them together and keep it straight, then you can develop a line. So like I already drew a representation of a line on here, but think about the line as consisting of you have this point, and then you draw another point next to it, draw another point next to it, draw another point next to it, another point next to it, and eventually you keep stringing these together and keep it straight, and you do this infinitely in opposite directions, and you end up with a line. So a line by its definition is straight, so it's redundant to say draw me a straight line. Because by its definition a line is straight, so you don't need to say straight line. If it's not straight, then it's a curve. And then also you really can't truly draw a line because even though I drew a representation of a line here, this is not an actual line because this has width. I can get down in there and measure the width, even though it's teeny tiny. But in the real concept of a line, there is no width because remember, points have neither depth, width, or breadth. No radius, basically. And there's no gaps between the points in a real line. And in reality, if you look really closely at this, there's probably gaps because of pixels and stuff. And then the representation, we put the little arrows to show that it continues in that direction. So this line representation shows us it continues infinitely in opposite directions. Now if you start putting lines together side by side, these are not straight, but you get the idea. You start putting lines together side by side, eventually you can build something that has like a length and width. It won't have a height because a line has neither width, doesn't have a width. The points that make up don't have width, depth, breadth. But just think about this as a piece of paper with no thickness. I know it can't exist because if you make a piece of paper, it's going to have thickness. But think about it as like this sheet of paper, no thickness, that keeps going up in all directions, and both length and width are infinite. That's what a plane really is. But I hope you're starting to see why these are undefined terms, because you really can't point to something and say, well, by definition, this is what this is. You can describe it, you can draw representations of it, but can't truly have it. But these are the essence of where we start with geometry. Alright, so back to lines. We talked about points, lines, and planes. Back to lines. We talked about how you could draw a representation of a line like so. If we want to name a line, we need to identify 2 points on the line. And when you name points, usually you use capital letters. I wish you'd just let me draw the stupid point. Instead of doing that. Don't want the menu. I want a dot. Oh my gosh, I don't know how to make it stop doing that. But anyways, you draw your points. That's PowerPoint doing that. It thinks it's a mouse clicking, I think. But you draw your points on there, and that's the way you can identify a line. Any 2 points that are on that line, you can figure out where they are, and the names are capital letters. And with symbolism, you can symbolize the line by saying this, and that would be red line AB. So symbolic notation, you'd name the two of the points that are on the line. Any 2 points, doesn't matter what two. And A and B are not the only 2 points in that line, because remember it's a string of infinite points. But yeah, A and B, and you put the little line symbol above it, and that's line AB with symbols. Now if you take a line and you put a point in it. That point divides up the line into 3 parts. So let's put 2 more points on here so that we can talk about this. Divides it up into 3 parts. We got point C, and then we have half lines. It divides it up into 2 half lines. We have half line CD, and then we have half line CE. Notice that the half line, there's an open circle here above the C, and it has an arrow above the D and above the E. Well, since I was talking about it dividing up into 3 parts, one of the parts is point C, and then the other 2 parts are the rest of the line without point C. So half line CD is this side of the line, not including C, and half line CE is that side of the line, not including C. So you put the little open circle over C, which is where the half line starts. That doesn't include C, but it starts right after C, and then you put the arrow over a point that the half line goes through. And that way people know what direction you're looking at. Those are the 3 parts of a line when you have a point in there dividing up the line on the line there. Now if you have what looks like a half line that includes your beginning point, then you have something called a ray. So if a solid dot with the line with like a half line going out from there, but including that dot, then you have a ray. I like to think about this as like the sun's rays. The light coming from the sun starts at the sun, so like point F could be the sun. And then the rays go out and go straight from that until they hit something. That they can keep going if nothing interferes, and they will just keep going infinitely straight in one direction. So that's what a ray does. It starts at a point and just goes straight in one direction. And then to name it, it helps to have another point it's going through so that people can see what the starting point is and then what point it's going through. More parts of lines. Often when somebody says, hey, draw me a line, what people do is they actually draw a line segment. Line segment has beginning and ending points. It doesn't extend infinitely in both directions. If you want to use symbols for a line segment, just do that. This is line segment HJ. Now you can talk about line segments without their endpoints, and then you have something called an open line segment or a half open line segment. Open line segment is a line segment that does not include the 2 endpoints. So symbolically, you would put the 2 endpoints and then put the little line segment symbol, but with little open circles on the ends. So this is an open line segment KL. Or if it's only if one point's included and the other is not, then it's a half open line segment. So you use the endpoints. Make sure you leave an open circle above the endpoint that's not included. And like this one, the open circle would be over the P. Wish it wouldn't do that. Gosh. People aren't going to be able to look at that later and see what it's doing, what it's supposed to be doing. Let's try that again. Like that. So you have the half open line segment PQ there. In that case, the P has the open circle. But those are all different parts of lines to be familiar with. Know how to identify them, know how to use the symbols for them, know what they're called. Okay, now in your text, there's some homework problems where you have to work with shapes and trying to figure out what's going on with those. One particular problem has this image with 3 lines intersecting each other. These 3 lines intersect and do form a triangle too. And the various points of intersection are named, as are other points that the lines are going through. Now if you want to reference this, the current textbook has it on page 444. It's for exercises 19 through 30. Alright, there you go. So then it has you take this image and then try to identify what's going on with some various unions and intersections. Okay, for example, you might be asked something like, we got ray AB, and what's the intersection with ray DC? Okay, so you got ray AB. In other words, you're starting at A, going through B, and then going on to infinity. You're seeing about the intersection with ray DC. Well, ray DC starts with D, goes through C, and then goes to infinity. So you're trying to see where's the intersection of those. It might help to have a different color in there. So let's do ray DC in a different color here. So where's the intersection? So where do they overlap? In this case, you're looking at what's both red and black at the same time. Well, starting at A, we've got the black point A, but we've also got the red ray going through point A. And then through B, it's both black and red. Through C, it's both black and red. Through D, it's both black and red. And then after D, it's just black. So for the intersection or overlap, it helps sometimes to do little tricks like put things in different colors. And you can say, well, where do both colors occur at the same time? Well, both colors occur starting at A, ending at D for that line segment. So that's where the intersection is occurring. So you want to be able to figure out where that overlap is and then symbolically tell us what that shape is. Okay, here's another one that says half line FE union ray FG. Often for unions, I'll just use the same color because you're trying to look at what does it look like when all is said and done. When you put the two together, what kind of shape do you have? Okay, so there's our half line FE. And then our ray FG, our ray will include F. Stop that. And it goes through G. As long as one of them includes it in a union, the whole thing counts. So like one of them includes point F in this union, so point F is going to be a part of the final answer. And notice that when you put it all together and step back and look at the big picture, you actually have a line here. You actually have line EG. Now just to let you know, this same line can be identified other ways. You could call it line GE. You could call it line EF. You could call it line FE. You could call it line GF. FG. These are all ways to identify the same line. Just pick one of them. It doesn't matter which one you pick. As long as you pick 2 points on a line and then put the little line symbol over it, then you're referring to that line. Okay. What are we going to talk about next? We're going to talk about parallel and skew. Definitions here. Well, parallel lines. I think you guys have all heard about parallel lines before. They are lines in the same plane that do not intersect. Okay, so L1, line 1, is parallel to L2. Little parallel bars is the symbol for parallel to. It should be in the same plane, not is. Lines in the same plane that do not intersect. Parallel planes, same kind of concept. Like if you picture a closed box, opposite sides of the box can be thought of as representations of parallel planes. So you got that, like the top and bottom there. They're planes that do not intersect in space. Then skew lines. Skew lines do not intersect, but they're in different planes that do not intersect. Lines in different planes that do not intersect. Okay, so like if you're talking about your box, it's like a little finite representation. You think about edges, like let's say this back edge here. And let's say you talk about this front edge here. Those are skew lines because the front edge of the box is going up and down, back edge of the box here is going side to side. They never touch each other. They're in different planes in space, and they're not going to cross each other. Those are skew lines. Okay, now going back to our parts of a line, let's say we take two rays and give them a common endpoint. So let's say we take ray AB and put it with ray AC. So it's the union of ray AB with ray AC. We call angle BAC, or we can call it angle CAB, or you could call it angle A using what's called the vertex. Usually, though, I suggest using the 3 letters, so that way people know for sure what angle you're talking about, especially when you start getting into more complicated figures where you might have several angles with the same vertex or something. But the vertex is the starting point, that common endpoint. So in this case, it's that point A. And then the sides of the angle are the rays that make it up. So ray so you got ray AB is one of the sides of this angle. Ray AC is the other side of that angle. All right, measuring angles. Trying to measure angles or look at their size, you can use degrees, radians, or gradians. We're going to focus on degrees, keeping in mind that, like, what is a degree? Well, if you take a circle and divide it up into 360 equal parts, each angle will equal 1 degree. Why 360? Well, for some of the folks who were first setting up some of this mathematics, calendars and dates were a very important thing to them. It was often integrated into their religion and other, obviously daily life too, like it is for ours. And at the time, they believed that there were 360 days in a year. 30 days in a month times 12 is 360. So they like to use 360 in things. There's actually a number system too, an ancient number system. If you take MGF 1107, you might learn about it, depends on your teacher. But they were a base 20 number system, except when it came to 20 squared. They wouldn't use 400, they'd use 360. And then after that, they'd resume multiplying by 20s. And they had to work that 360 in there because to them it had that significance of how many days in a year and ties to their religion. Now for us, since we're dealing with degrees, if you want to deal with radians and gradients, go take other math classes like trig. But since we're dealing with degrees, we're going to also need to be familiar with just what a protractor is. It's a measuring tool for angles. And we use it to measure degrees. And here's 4 of them. Here's pictures of 4 of them. Let's say you want to have an angle that's 72 degrees. Well, you can have you line up one of your rays with 0 here. And line up the starting point, the vertex, right here. And then since you're using this side for your initial side, using this part of this protractor for your initial side, you're going to go up along the protractor. Notice that the numbers go up on this bottom scale. So use that bottom scale, find 70, and then each little mark is 1. So 72, you got 1, 2, right here. Oh my goodness, I can't stand how it keeps doing that. And then, so your other ray is going to go up through there.
it's not cooperating. Sometimes it lets me, sometimes it doesn't. I don't understand this. I'll just draw it with like little strokes. There we go. So 72 degrees will go there. Alright, let's say you want 106 degrees. And let's say this time your ray, you want to put your initial side, one of your rays here. Well, notice that coming from there, going on the protractor, you have to use the top scale to count up. There's 100. The slightly longer mark in between is 5. So 105, and then the one next to that is 106. So there you go. 106 goes. I'm not even doing it in a circle, and it's still being annoying. Oh my gosh. So 106 goes right there. So you can either use the protractor to help you draw angles, or you can use it to measure angles. Just make sure that your vertex is lined up down here at this little middle part. Or usually there's like a little hole cut out in a plastic protractor. Make sure your initial side's lined up with 0, either direction, and then your terminal side is the other side where you're going to have it marked at the degree measure. Okay, a couple of problems we might do. Let's see here. Dealing with angles. Got another image. This is also on page 444 in the current text. There's 3 lines that intersect each other. And there's some various points on those lines. Okay, we've got line DBE. We got line ABC. And we've got line FBG. Alright. Let's see here. Let's say we have a question like angle ABD intersects angle CBG. Okay, so we got angle ABD. Looks like this. I like to just redraw the parts I need and skip everything else. Can't have it drawn those random segments. It messes up the image and makes it a different picture. ABD. And we want to see where this intersects CBG, so let me change the color here. This is red. So CBG looks like this. Okay, so remember with intersections, you are just looking at where they overlap, where they have the same stuff. And in this case, the only overlap is at point B, because everything else is either solid black or solid red. At point B, you've got both the black and red there existing together. So point B, you just draw a little point, and then name it B. So point B. So that is the only place where you have that intersection occurring. Alright, another question would be something like half line BF. And we're doing the union with ray BE. Okay, half line BF looks like this. So remember, half line, you're not actually including that starting point. And then ray BE, in an array, you are including that starting point. And since this is a union, I'm just going to use the same colors because I want to see the big picture. What does this look like when I'm done drawing it? Well, when I'm done drawing it, the union, putting everything together, makes an angle. You can say that this is angle FBE, or you could call it, or you could say that it's angle EBF. You can either go FBE or EBF, doesn't matter. It's up to you. There you go. There's examples of some angle problems. Alright, some other types of angles. Some different types of angles. Right angle. Measurement equals 90 degrees. So a right angle, you draw that. You need to let people know that it's 90 degrees because otherwise they don't know if it's 89.9. So you can draw like a little square corner there, or you can just tell people that the measure is 90 degrees. Acute is more than 0 and less than 90. So, it's a smaller angle. I think small things are cute, so it's an acute angle. Obtuse, more than 90 and less than 180. Notice that 180 would look like a line, basically, if you drew that angle. So obtuse is pretty big. More than 90 but less than 180. And then straight equals 180. Basically, when you put the angle the two rays together, they make a line. The union of these two rays makes a line. And you can see if you want to draw 180, it's straight across down here. More types of angles. Adjacent angles are angles that share the same side. So let's say you have this. Okay, so angle PQR and angle RQS are adjacent angles. They share the side QR. Share that ray QR. Vertical angles, if you have two lines that intersect, vertical angles are angles that are opposite of each other. So let's say you have angle LMN right here, and PQ. So angle LMN and angle PMQ are vertical angles. And vertical angles are always congruent. In other words, they have the same measure. So the measure of angle LMN equals the measure of angle PMQ. Or you could say that angle LMN is congruent to angle PMQ. That's the same measure. But also angle LMP and angle NMQ are vertical angles. because they're on opposite sides there. So LMP is congruent to NMQ. And their vertical angles are opposite, the angles opposite each other on intersecting lines. Complementary and supplementary. Complementary measures add to 90 degrees. Supplementary measures add to 180 degrees. Little hint. C before S in the alphabet, 90 before 180 in the numbers. Because I know it's so easy to get confused which one's which. It's like, is it complementary or supplementary was 90 degrees? Well, just remember C comes before S in the alphabet, 90 degrees comes before 180 in the numbers. All right, let's look at an example with those. Let's say that you're told the angles are complementary. You're given a figure that looks like this. Basically, you're given a right angle that's made up of two adjacent angles. Angle 1 and angle 2. And you're told that angle 1 is x degrees and angle 2 is 5x minus 6 degrees. Well, since they're complementary, the measure of angle 1 plus the measure of angle 2 has to equal 90 degrees. So that x degrees for angle 1 plus the 5x minus 6 degrees for angle 2 has to equal 90 degrees. So you got a basic algebra equation you got to solve here. X plus 5x is 6x. Add 6 to both sides and you get equals 96. Divide by 6 on both sides, x equals 16. So the measure of angle 1 is 16 degrees. And then for angle 2, you can either do 5x minus 6, which is 5 times 16 minus 6, 80 minus 6, which is 74, or you could just say 90 minus 16, and you get the same thing. So the measure of angle 2 is 74 degrees. Sorry about that. And 16 and 74 do add up to 90 degrees. All right, what if they say something about supplementary? Angle 1 and angle 2 are supplementary. Measure of angle 2 is 17 times the measure of angle 1. Determine the measures of the two angles. Alright, so since they're supplementary, we know that the measure of angle 1 plus the measure of angle 2 has to equal 180 degrees. Now, measure of angle 2 is 17 times the measure of angle 1. Let's let the measure of angle 1 equal x. So the measure of angle 2 is 17 times that, or 17 times x. So x plus 17x equals 180. 18x equals 180. Divide both sides by 18. X equals 10. And then you can say either 17x or 17 times 10 equals 170. Or you can say 180 minus 10 is 170. So the measure of angle 1 is 10 degrees. Measure of angle 2 is 170 degrees. And those two add up to 180. All right, last concept in this lesson. Parallel lines. Parallel lines intersected by transversal. Transversal is a line just intersecting two parallel lines. So this line here is the transversal. So L1, line 1, is parallel to L2, or line 2. Let's go ahead and label the angles that are made with numbers. That's another way that you can name angles. Okay, and there's some relationships with these angles here. Since the transversal is intersecting each of those parallel lines at the same angle, the angles that are formed are related to each other. All right, alternate interior angles. On the inside of the parallel lines, angles on alternate or opposite sides of that transversal are alternate interior angles. You got angle 3 and angle 6. You've also got angle 4 and angle 5. Now in alternate interior angles, the measures are the same. The measure of angle 3 is going to equal the measure of angle 6. So in other words, angle 3 and angle 6 are congruent. The measure of angle 4 is going to equal the measure of angle 5, because those are congruent. Alternate exterior angles. Exterior, so going out from the parallel lines. 1 and 2 and 7 and 8 are exterior angles. Alternate exterior are on alternate sides of that transversal. So like angle 1 and angle 8, or like angle 2 and angle 7. And again, alternate exterior angles are congruent to each other. The measure of angle 1 is equal to the measure of angle 8. The measure of angle 2 is equal to the measure of angle 7. And then corresponding angles are in the same position related to each other. For corresponding angles, you got angle 1 and angle 5. You got angle 2 and angle 6. You got angle 3 and angle 7. You've also got angle 4 and angle 8. Those are corresponding angles. And each pair is congruent here too. So alternate interior angles, those pairs are congruent. Alternate exterior angles, those pairs are congruent. Corresponding angles, those pairs are congruent. All right, let's look at a problem where you have to deal with parallel lines in a transversal and trying to figure out missing information. You have an angle here that's 130 degrees. And it's our job to fill out the rest of the angle measures. There's all kinds of relationships you can use to fill these out. For instance, I can put 130 degrees right here because these two are corresponding angles. They're going to have the same measure. I can also put 130 degrees right here, because these two are vertical angles and have the same measure. Or I could say that these two are alternate interior angles and have the same measure. I could put 130 degrees here. We've got vertical angles, we've got corresponding angles, or we've got alternate exterior angles. All of those reasons for putting 130 right here. All right, what are we going to put there? Well, this angle and this angle, these two adjacent angles together, help make this straight angle, or 180 degrees. So 180 degrees minus 130 degrees gives me 50 degrees. And for the same reasoning, I could put 50 degrees here. You have the straight angle, or all the way around makes 360. 50 plus 130 plus 50 plus 130. 50 and 50 here are vertical angles and are thus congruent. I can put 50 here for the same reasons, but I can also say these two are corresponding, these two are alternate interior. I can put 50 here for the same reasons, but I can also say these two are vertical, these two are corresponding, these two are alternate exterior. So all kinds of reasons for why I can fill that in that way. Okay? And notice that when you look at these angles and these angles, they look the same, because that transversal is intersecting the lines in at the same angle in both cases. All right, well, I think that's enough foundations for now. Sort of, building up some of these concepts that you're going to be using throughout the rest of this unit and the next unit on geometry. So make sure you're doing plenty of practice, especially with filling in missing angles and doing unions and intersections, because you just might see some of those on your next test. So make sure you get plenty of practice with that, and tune in next time for us to start talking about polygons.